Alright, so, hey, this is Joe, and this is the third video of the 14th chapter of Stewart's Calculus, and we're going to be talking about tangent planes and differentials in multiple functions with multiple variables. So, in your book, you're given this formula, and you're given a proof for this formula that I'm not going to bother going through right now. Your book does a good job of it. For the tangent plane, tangent to a surface z is f of xy at some point described like this, and that tangent plane can be expressed by the equation z is equal to the partial derivative of f with respect to x at point x sub 0 y sub 0 times x minus x sub 0 plus the partial derivative of f with respect to y at x sub 0 y sub 0 times y minus y sub 0 plus the initial z value, the starting point of the point right here. And this is basically just our normal equation of a plane. However, instead of where the components of our normal vector should be, we have the x component of our normal vector is this partial derivative with respect to x, the y is the y component with respect to y, and the z component of the normal vector is 1. And we can prove this formula a couple ways, algebraically, as in the fashion that your book did, or we could calculate the normal vector given unit tangent vectors of the surface at this point, which would end up involving both of these partial derivatives, then find the normal vector, and then find its components, and get this equation right here. But we're not going to do any of that. Just remember this equation, and you should be good. So we're going to do one little practice problem right here, solve finding the tangent plane to a surface, and I'll show you on a graph kind of what that looks like. We're going to start off with question number 4 on page 946 in your book, and this question asks us to find the tangent plane to the graph of this function at point 202. So first we're going to do the algebraic solution for this problem, and then I'm going to show you what this graph and the tangent plane look like on a graph. So first off, we're going to start with our equation right here. We have z is going to be the partial derivative of f with respect to x at, in this case, 0 times x minus, and then our starting point for the point we're differentiating at is going to be 2, so x minus 2, plus the partial derivative of x with respect to y at 0 times y minus, and our y coordinate of the point we're differentiating at is going to be 0, so y minus 0, and then plus our 2, the y coordinate of the point we're differentiating at. So now we need to find, take both of these partial derivatives right here. So let's start off with the partial derivative with respect to x, and so we're taking it, of course, out of this equation right here. And so we're going to need to use our product rule here because we've got two functions of x multiplied by one another. So first we're going to leave the x alone, and we're going to take the derivative of the y, the e expression right there. So we have our x, and when we take the derivative of this e expression, we treat the x as the variable and the y as the constant, and so the y is going to come out as the derivative of xy. So we'll have an xy down here times e to the xy, plus, now we're going to take the derivative of the x right here, and that'll be a 1, and we're going to leave this guy alone, and so that'll be an e to the xy. Now we're going to take and so now we're going to have to plug in for points 2 and 0 because we're taking this partial derivative at that point, since this is the point we're trying to find the plane that's tangent to it. So we'll get the partial derivative of x with respect to y at point 2, 0, and now we just plug in the 2's and the 0's for our x's and y's. So this term is going to become a 0 because we have that 0 in the y, so that'll be a 0, and then e to the 0, because this exponent will become a 0, is that will end up being a 1. So we have a little 1 like that. Now we will find the partial derivative of f with respect to y. So I'll just kind of underline that right there. Now, what we have to do is we don't have to use our product rule here because this x we just treat as a constant. So we keep that x out there. We take the derivative of this e expression with respect to y. This x is a constant. So we'll bring that x out here into the coefficient, and that'll give us an x squared times e to the xy. And now we have to find this derivative at point 2, 0. So that'll be del f del y at 2, 0. So we plug in a 2 for the x right here, and we'll get a 4. And then this e to the 0, because the 0 will come in with the y, is going to be 1, so that'll just be equal to 4. Now we can start plugging this all into our equation of a plane right here. So we'll get z is equal to, that is a 1, so we'll just get x minus 2 plus, and then this partial derivative right there is a 4, so we'll plug in a 4 for the coefficient, and we'll get y minus 0 plus 2, and that is the equation of the tangent plane. Now let's go see what that looks like graphically with our little graphing software. Alright, so here is our equation right here. Oh, sorry, that is the tangent plane. So here's the curve, x times e to the xy, and here is our tangent plane, and let's make that appear right here. And we see this is the x-axis. Our 2 is going to be, here we can actually zoom in a little bit and take a look at that. So our 2 is going to be about right here, and our 0 on the y-axis, so we're going to be just talking about the x-axis right here, and we see that at that point, which is about right there, we can actually zoom out a little bit, it does, oh, now we're a little too far away, sorry about that, folks. There, so this is about 2, 0 right here, and then up 2, because it's 2, 0, 2 is the point at which we're trying to find the tangent plane, and that's about right here, and that looks about right. That looks to get the slope of the surface at that point just about right. So that's how graphically you should be thinking about tangent planes to curves at points. So now let's go back and we can talk about differentials of a function now that we know about tangent planes. So in single variable calculus we deal with two differentials. We deal with dx and dy. And dx is analogous to a change in x, but the d comes in when we make that change approach 0. So this comes in when the change of x approaches 0. So very, very tiny changes. And dy, I should say, is analogous to a change in y, but when that change in y approaches 0. And so on a two-dimensional graph, this kind of makes that we can make this dx correspond to a little tiny change in a width, and the dy corresponds to a little tiny change in height. And that's pretty intuitive. However, in multivariable calculus, when we have these two independent variables, sometimes we want to not only talk about slopes changing in certain directions, but the general differential with respect to z, a dz. So basically that means as we move a couple points in the coordinate xy plane, how much is z going to change? And what's that? And the d will come in when we make that change really, really small. So already we can think, well, this dz is going to be analogous to some change in z, but it's going to correspond to that when the change in z approaches 0. And that's a correct intuition. That's correct. And this change in z we can actually express as a formula. So the function, whatever the change in whatever function we're dealing with here, function in two variables, so some value a plus our change in x, and then our some value b plus our change in y minus the function ab. So this is our change in z. Basically all we're doing is we're changing both of our x and y coordinates by a little bit, so by something that's analogous to our x and y differentials. We're changing those by a little bit and subtracting the original value of the function to get some general change in z, and this dz is called our total differential once we make that change in z approach 0. So since we have changes in both of these, in this change in z when it approaches 0, it approaches 0 when our change in x approaches 0, and our change in y approaches 0. So basically, these changes are going to turn into our more familiar differentials. And because both of those differentials are going to be in both coordinates of this function, so we're going to have to do some nasty algebra to work this out and put it into partial differential notation. But I believe your book does that for you, and if not, you don't need to worry about that right now for this class. But we can, given that sort of conceptual analysis, I feel comfortable giving you the equation that our dz, our total differential, is equal to the partial derivative of z with respect to x times our x differential plus partial derivative of z with respect to y times our y differential. And that is our total differential. And this kind of makes sense, considering that we can express something similar in single variable calculus. Dy is equal to f prime of x dx, like that. Considering that this holds in single variable calculus, this kind of makes sense. If you think of our partial derivative, first order partial derivatives of z as our f prime, and our single variable differentials right here as analogous to our dx. That's just one way to kind of memorize this formula, make sense of this formula, and then using our little change notation is another way to think of that. So one thing that your book asks you to do a lot of is kind of compare calculating a change in z to calculating the differential with respect to z. And that's not going to be terribly practical if you're actually applying this kind of math, but it's a sort of interesting conceptual analysis. And one more thing about, and if you think, oh, well, we won't need to calculate, we'll only need to calculate the change in z if we have some a and b and some definite change that we know about. Well, you actually need both of those things to calculate the differential as well, because what do you do with, how do we calculate dx and dy? We don't have some single variable function like this. Well, in order to calculate that for our purposes in multivariable calculus, we're going to say that our dx is equal to some write that just as a change in x. So if some x variable is changing by some amount, to calculate the differential we calculate a delta x, and our dy is going to be a delta y. And this is a little bit crude, but for our purposes in multivariable calculus it works very accurately. But that means in order to calculate a differential you need to know these two changes, right? You need to know what these two differentials are. Otherwise we'd end up doing partial differential equations, which that's its own course by itself. So you can assume for multivariable calculus you will be given these differentials or some change in x and some change in y. And I'm going to show you a picture from your book right here that tells us why we're allowed to use a definite number in here instead of doing some calculus to calculate them. So our ultimate goal in finding a total differential is to find the difference in this height right here. And this height right here corresponds to the height between the plane in the z-axis, or bisecting the z-axis through our initial point right here, AB, between that plane in the z-axis and the tangent plane through that initial point to our surface. And that differential is going to tell us our change in z, or our very small change in z. So basically the change in z instantaneous at that point, right? This is obviously blown up a little bit. And so that's why, because the distance between those two corners is all we care about, we're allowed to use a change in y and a change in x instead of doing calculus to find this dx and this dy, because regardless this little cube is going to be tiny, 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 and it'll preserve the sort of instantaneous accuracy we're looking for in finding our dz. And our change in z ends up being a lot bigger. Yes, our change in z ends up being a lot bigger if we use our change in x and our change in y instead of our partial derivatives, because when you plug it into this formula right here, or you have a little f right there, as we were talking about earlier, actually it appears right here. When you plug that in, it actually creates a whole lot more error than when we're just using the change in x and the change in y for our differentials and calculating the total differential, because we are calculating this total differential as the difference between the height of the tangent plane, and that tangent plane, in order to calculate that, we need to use partial derivatives. And this distance is always going to be a lot smaller than the distance between the surface and this plane bisecting the z-axis, because the plane has a lot more change to it. So that's why we don't, it's less precise if we put our deltas inside the function to calculate the change in z than if we just use those deltas multiplied by partial derivatives to calculate our total differential. So that's kind of an explanation of why the total differential is still more precise than just calculating a delta z. So now let's do one little sample problem with our total differentials. So we're going to do number 37 on page 946 in your book, and this problem gives us a function in two variables. So t is a function of big R and little r, and big R and little r are drawn right here onto this yo-yo. So, and the t models the tension in the string of a yo-yo. And so m and g are both constants. The mass and the gravitational, the acceleration due to gravity don't change, so we can count those as constants. And so we need to use differentials to estimate the change in the tension when r, so big R, this big radius, is increased by 0.1 centimeters, and little r is increased by 0.1 centimeters. And one important thing to remember here is when we're calculating our partial derivatives, we want to calculate our partial derivatives, again, at the initial points. Remember our p, x sub 0, y sub 0, z sub 0, that's where we want to be calculating our partial derivatives. So our partial derivatives we calculate at 3.7, but the changes are kind of single variable differentials. You can think about our dy and our dx. We make those the change. We equate those to the change in x and the change in y, or the change in big R and the change in little r. So that'll be a 0.1 and a 0.1. So let's go over to the white screen and start solving this. Alright, so we're trying to find the total differential of t right here, like that. And so in order to find that, we're going to need to find the partial derivative of big T with respect to little r at, so our initial points, so at 0.7 and 0.3, and then multiply that by the change in little r, which is going to be a 0.1, and then add that to the partial derivative of big T with respect to big R, and that's going to be, then we're going to find that again at the initial points, so 0.7 and 3, and then multiplied by dr, which is equal to the change in r, and so that will also be 0.1. I can write that out here for you guys to see that. So now first we have to do some of our partial derivative work right here, and that's kind of a nasty partial derivative to calculate. You have to use quotient rule, or your product rule if you will, and so that'll equal, I'm not plugging in values yet, that'll be mg 2r squared plus big R squared minus 4mgr squared over 2r squared plus r squared squared, and all that multiplied by 0.1, plus, and then the derivative with respect to big R, partial derivative with respect to big R I should say, that's not a plus, that's a minus 4mg big R little r 2 little r squared plus big R squared squared, and all this times 0.1. Now all you need to do to find exactly what this differential is is plug in 0.7 for little r and 3 for big R. I'm not going to do that for you right now. I think you can figure out that algebra, but this is the derivative work and the conceptual work for you. So that's it for this video about tangent planes and partial, or not partial, just differentials in three variables. Partial differentials is even more complicated, and a little bit different, and more precise actually. Partial differentials, if we were doing real partial differential equations, we wouldn't need to make this assumption here, that's actually a little inaccurate, that dr and d little r is equal to the change in r and the change in little r. We'd be able to use partial derivatives, differentials, and it would be more accurate, but we're not, and that's not covered in this class, and that's a totally fine thing to do for the sake of this class. But in any case, that's it for those concepts. I hope you stay tuned for the rest of this course and the rest of the videos. Thank you for watching.